In this video, I'm going to talk about drawing diagrams for experimental setup in paper 5. So for those who have this compilation of paper 5 diagram questions, you can use these papers to practice the drawings after you watch the video. For every question, I've labeled the type of experimental setup that you need to draw. So by referring to the title, you'll be able to know what type of setup they're looking for. So for all paper 5 experimental setup question, I categorize them into 8 different types. Type number 1 will be collection of gas. So this setup will be for reactions which will produce a gas as a product. So there are two methods to collect gas. The left-hand side one is called collection over water. We need an inverted measuring cylinder and we need a water trough. Then the reaction in the conical flask must be tightly sealed so that we can deliver the gas using a delivery tube to the measuring cylinder. Then from the scale on this measuring cylinder, the graduations will be able to measure the volume of gas that is produced. Now the right-hand side is something that is simpler, which is collection by using a gas syringe. So this is much simpler and less messy because water trough is not needed. We need a delivery tube connected to the gas syringe. So directly we can measure the volume of gas by reading the gradation on the syringe. Now whenever you are asked to draw a setup to collect gas that is produced in a reaction, both methods will be acceptable. Just make sure that the flask must be tightly sealed. Make sure that there is no leakage of gas. So I've listed a few questions from past year papers. So go through the questions and suggest which apparatus should you use to collect the gas. Now some questions will actually specify which method they prefer you to use. So for the paper in winter 2022, the question actually asks for gas collection over water. If this is the case, then only the diagram on the left-hand side will be accepted as the answer. Drawing collection using gas syringe setup will make you lose marks. So you can try looking at the other two questions that I listed here also to find out which part of the question did they mention and specify which method to use so that you can get used to the style of the paper. Now there's this one very special question from summer 2014. In the question, students are asked to draw and label a diagram that is capable of absorbing nitrogen 4 oxide and acidic gas. You can try drawing the setup and come back and check your answer against mine. Now it is a question that is decomposing magnesium nitrate. Magnesium nitrate on thermal decomposition will form magnesium oxide, which is a solid, nitrogen 4 oxide, and acidic gas and oxygen. So we need to collect two different gases. Now the solid magnesium oxide form will stay in the boiling tube. The first one that we want to collect is nitrogen 4 oxide. So we make the gas to go through sodium hydroxide solution. Because sodium hydroxide solution is an alkaline solution, it will be able to react with nitrogen 4 oxide. So nitrogen 4 oxide will be absorbed by NaOH. Oxygen, which will not react with sodium hydroxide, will go through the other delivery tube to water trough here or gas syringe. If you draw a gas syringe here, then the volume of oxygen can be read separately. So I'm showing you this question because the question asks for another method of collection of gas, which is by absorption. So here will be a list of questions from 2014 until March 2024, which are asking for a diagram for collection of gas. Some of them are just collection of gas, and some of them are combination of different types of setup. But after I go through all types with you, then you'll be able to combine them in the same diagram. Second type will be separating chemicals before experiment. Separating chemicals before experiment usually involves reaction with two different reactants in different states, usually an aqueous solution and a solid, and also a gas will be produced as a product. Now let's look at this setup. This is reaction between hydrogen peroxide and manganese oxide. Oxygen gas will be produced. Now we do not want to lose any gas before the reaction occurs. If we do not separate the chemicals, we have to make sure that we close the bunk very quickly to minimize loss of gas. But by separating the chemicals before the reaction, we put the solid in a small tube that can fit into the chemical flask. Then the other reagent, which is the aqueous solution, is separated from the solid reactant in the conical flask. A string is tied over this tube and make sure that it is long enough that we can reach the string after we fit the bunk. Now fitting these bunks is sealing the reaction mixture for the reaction. So once everything is ready, nicely set up, we can pull the string so that all this solid will fall into the solution. Reaction will start. So not a single gas molecule can escape from this system because it's tightly sealed. So all gas will go through this water and be collected at this measuring cylinder. So if you are asked to draw an experimental setup which involves two reactants, one of them is solid, the other one is solution, and a gas will be produced, this will be the setup that you're looking for. Right, so these are the questions in the past papers that you can practice with drawing experimental setup to separate chemicals before reaction. Step number 3 will be controlled temperature experiment. I will further split this controlled temperature experiment into 3 subcategories: low temperature, around room temperature, and high temperature. Now, low temperature means they want to conduct the experiment at temperature lower than room temperature. So our room temperature is 25 degrees Celsius. So any temperature lower than 25 is categorized under low temperature. Now around room temperature will be 25. So before the boiling point of water, I'll put 80. And high temperature means higher than boiling point of water. Let's look at one experiment from a March 2018 paper. Now this is an experiment that they want you to carry out at 6.5 degrees Celsius. Freeze pure liquid cyclohexane. So that will require a temperature that's lower than 25 degrees Celsius. So to achieve temperature lower than room temperature, we will need ice water. So draw a container and then ice cubes with water higher than liquid level here to make sure that we can freeze all cyclohexane. Now the container that we use is also important because we want it to be an insulator. So label it as plastic cup and then label ice in water as ice water bath. So for any experiments with temperature lower than room temperature, we use this same setup. Right, another experiment which they want to investigate the reaction at 30 degrees Celsius. So that will be temperature around room temperature. Falls within the range that I gave you just now, 25 to 80. To achieve a constant temperature at 30 degrees Celsius, the best method would be using a thermostatistically controlled water bath. So draw a box like this with water surrounding the conical flask. Label it as thermostatistically controlled heater and then write the temperature of the water bath. Put a thermometer to monitor the temperature. So that will be how we maintain a temperature 25 to 80 degrees Celsius. Now, Bunsen burner will not be allowed for this type of experiment. Using naked flame is not a good idea because we cannot control the temperature of the water. Now, sometimes in the mark scheme, we'll put electrical heater as an option, but from all the examiners' report that I've read, the best answer is still a thermostatistically controlled heater. Right, so that category will be high temperature higher than boiling point of water, and the only method to achieve very high temperature will be using direct heating from Bunsen burner. Usually for decomposition of carbonate or nitrate of a metal, we use Bunsen burner because we need very high temperature to make them decompose. So here is the list of questions which temperature needs to be controlled in the experiment. Category 4 will be enthalpy change experiments. In experiments involving enthalpy changes, we will use calorimetry, which is a polishing cup with a lid and also a thermometer soak in the reaction mixture to measure the temperature change throughout the whole experiment. Now this setup is quite straightforward. You may go through all these questions from the past papers to practice drawing this calorimetry diagram. Now this is a diagram from a Winter 21 paper. What is missing will be the lid to prevent heat loss to the surrounding. Now let's look at the fifth type of diagrams, filtration. Now there are two types of filtration. One is a very simple filtration that we always use in the lab, which is called gravity filtration. We use a funnel, line it with folded filter paper, and pour the mixture with precipitate and get our filtrate and residue after the filtration. Now the one on the right hand side is called filtration using reduced pressure. We are using a Buchner flask and funnel, and the side arm of this flask is connected to a vacuum pump. So vacuum pump will remove all the air inside the flask. It will make the pressure inside the flask very low. So the air outside now has higher pressure than inside, will press the solution down. It will make the filtration process faster. And also at the end, we actually get drier solid compared to gravity filtration. Now this funnel is something that looks like this. It has holes, so we need to line a piece of filter paper to collect the residue. So there's a question in March 2019 paper asking us to complete a diagram to show how the student could filter the mixture under reduced pressure. So draw a Buchner funnel with a piece of filter paper in it, seal the flask so that the vacuum pump can suck all the air. I would also like to include this question, is also asked in the same paper. Suggest one major advantage of filtering the mixture under reduced pressure compared to filtering using gravity. By using filtration under reduced pressure, it is faster and the precipitate that we get is drier. Right, 3 more types to go. Number 6 will be experiment involving loss in mass. There will be 2 types of experiments. The first one is decomposition of carbonate or nitrate or hydrated compounds using a crucible. And this would be the setup that you draw. Now here they say show how loss of solid during heating will be prevented. That's why a lid is needed. If not, you can draw using crucible without a lid. Now another type of experiment would be reaction between acid and carbonate. Right, the reaction mixture will be in a conical flask or any container. Because the product is carbon dioxide gas, so we can just put the container containing the reaction mixture on a balance and monitor the mass change over time. Type 7, electrolysis and electrochemical cell. So we first need to know the difference between electrolysis and electrochemical cell. We have learned it in the A2 Electrochemistry chapter. The one on the left hand side will be an electrolysis, the one on the right will be an electrochemical cell. So the difference will be for electrolysis, both electrodes are in the same container. For electrochemical cell, you have 2 half cells. In electrolysis, you are using batteries and an ammeter. On the right hand side, electrochemical cell, we are using a voltmeter. So there's a question from summer 2015. They gave the reaction during electrolysis. So You must be able to deduce which is the cathode and which is the anode, because usually in this type of diagram, they will want you to label the electrodes. So use your knowledge that you have learned in the A2 syllabus to identify the cathode and anode in electrolysis. And then the question also say that you must be able to show how you could measure the current, which is by using an ammeter. You could collect gases, and then starting from this DC power supply, you draw your setup. So I have my diagram for this 2015 question, an electrolytic cell. So starting from this part, DC power supply, positive will be the anode and negative is the cathode. So I make sure that I have my half reactions correct on both sides. I'm collecting hydrogen gas here on the right hand side, and also heating gas on the left hand side, together with sodium hydroxide to absorb the acidic gaseous product. And here I have my electrolyte, the potassium butane dioate. But there's another question in summer 2018, which is also asking for diagram for an electrolytic cell. Now this time, they didn't give the DC power supply as a starting point, right? So you need to include that in your diagram. Now you can draw like the one given in the previous question, or you can use batteries. Now, I personally prefer to draw this DC power supply because I find it very difficult to remember the longer and shorter lines for the positive and negative terminal for the batteries. By drawing DC power supply like this, I only need to label one of them as positive and the other one as negative. Then by using panic, right, I know the positive one is for the anode and negative is for the cathode. Then I'll be able to draw my electrolytic cell. Now, this will be my answer for the summer 2018 question. So you can draw a diagram and then compare mine with yours. Right, for electrochemical cells, so far I've not found any question in paper 5 which is asking for you to draw a diagram, except for this very simple diagram that is asking you to label different parts of the electrochemical cell. So this circle here is a voltmeter, and then this one in the middle connecting both half cells is the salt bridge. So here will be a list of questions for electrochemistry experimental setup, which you can try. But I think I've gone through 3 of them. The last one will be condenser. Right, before we draw a condenser, we need to know that what is needed in the experiment is for heating under reflux, or it is for distillation of a liquid. For reflux condenser, it needs to be straight like this. So because using condenser in a reflux experiment is to prevent the loss of volatile organic compounds. We make sure that it won't dry up because of the heating, and at the end we get no products. Right, for distillation, the condenser is set up like this with an angle moving down. This one is to collect product once it is formed to separate it from reacting mixture. Now, this question from summer 2018, we are given a reflux condenser and you're supposed to label water is going in to the condenser from the lower side arm or the higher side arm. So water is always entering through the lower one for both reflux and also distillation, because water going in from the lower arm will make sure that water can stay longer inside the condenser for cooling purpose. So this diagram here is actually not correct. Water in should be from the lower side arm, water out from the higher one. Another question in summer 2019 for distillation, we are given the reaction mixture and then another flask for collection. So this is an experiment to show how propanol can be separated from the mixture. So inside the mixture, there are 2 compounds, propan-2-ol and propanol. The boiling points are given. Propanol with lower boiling point will form vapor first. So when the vapors are going up, we'll go through this condenser. This part is cold, so the propanol vapor will condense and become liquid propanol, which can be collected in this flask. So when you complete the diagram like this, there is a tube going up, and there's a thermometer here to measure the temperature, level water in and out also, and a few lines to represent water inside the condenser. And lastly, there's this list of questions to show you which past papers that you can practice your drawing for the condensers.